A bitch, nigga. A bitch, nigga. A bitch, nigga. Why you petty? Treat me like white tea. Don't get me dirty. Bubble, bubble me. Oh. Treat me like white tea. Don't get me dirty.
Get a loss of 3.15. We can generate from that. And we get something that is less garbage.
I'm that nigga from the treat me like don't get me dirty. मैं भाई क्या है यार, इतना धीरे क्यों चल रहा है?
You know, it has some next line characters. It understands a little bit more to, space things out and whatnot. So that's like slightly less garbage than before, but yeah, this is pretty good. So I lied. There aren't actually any lectures previously where I talked about optimizers, so might as well talk about it now. So we have a bunch of common ones, and honestly, you don't really need to know anything more than the common ones because most of them are just built off of these. So you have your mean squared error, common loss function used in regression problems, where it's like, you have a bunch of data points, find the best fit line, right? That's a common regression problem. Goal is to predict a continuous output. It measures the average squared difference between the predicted and actual values, often used to train neural networks for regression tasks. So, cool. That's the most basic one. You can look into that more if you'd like, but that's our most basic optimizer. Gradient descent is a step up from that. It's used to minimize the loss function in a model. It measures how well the gradient measures how well the model is able to predict the target variable based on the input features. So we have some input X, we have some weights and biases maybe, Wx plus B, and all we're trying to do is make sure that the inputs, or make sure that we make the inputs become the desired outputs, and based on how far it is away from the desired outputs, we can change the parameters of the model. So we went over gradient descent recently or previously, but that's pretty much what's going on here. And momentum is just a little extension of gradient descent that adds the momentum term. So it helps smooth out the training and allows it to continue moving in the right direction, even if the gradient changes direction or varies magnitude. It's particularly useful for training deep neural nets. So momentum is when you have, you consider some of the other gradients. So you have something that's like maybe passed on from here, and then it might include a little bit of the current one. So like 90%, like a good momentum coefficient would be like 90% previous gradients and then 10% of the current one. So it kind of like lags behind and makes it converge sort of smoothly, if that makes sense. RMS prop, I've never used this, but it's an algorithm that uses the moving average of the squared gradient to adapt learning rates of each parameter. It helps to avoid oscillations in the parameter updates and can improve convergence in some cases. So you can look more into that if you'd like. Atom, very popular, combines the ideas of momentum and RMS prop. It uses a moving average of both the gradient and its squared value to adapt the learning rate of each parameter. It's often used as a default optimizer for deep learning models. And in our case, when we continue to build this out, it's going to be quite a deep net. And Atom W is just a modification of the Atom optimizer that adds weight decay to the parameter updates. So helps to regularize and improve generalization performance. We'll be using this optimizer as it best suits the properties of the model we'll train in this video. So, of course, I'm reading off the script here. There's no really better way to say how these optimizers work, but yeah, if you want to look more into concepts like momentum or weight decay or oscillations and just some statistic stuff, you can. But honestly, the only thing that really matters is just knowing which optimizers are used for certain things. So, like, what is momentum used for? What is Atom W great for? What is MSE good for, right? Just knowing what the differences and similarities are, as well as when is the best case to use the optimizer. So yeah, you can find more information about that at torch.optim. So when we develop language models, something really important in language modeling, data science, machine learning at all, is just being able to report a loss or get an idea of how well our model is performing over, the first 1,000 iterations, and then the first 2,000 iterations, then 4,000 iterations, right? So we want to get a general idea of how our model is converging over time. But we don't want to just print every single step of this. That wouldn't make sense. So what we actually could do is print every, 200 iterations, 500. We could print every 10,000 iterations if you're running a crazy big language model if you wanted to. And that's exactly what we're going to implement right here. So actually this doesn't require an insane amount of Python syntax. This is just, I'm actually just going to add it into our for loop here. And what this is going to do is it's going to do what I just said, is print every certain number of iterations. So we can add a new hyperparameter up here called eval iters. And I'm going to make this 250 just for, just to make things sort of easy here. And we're going to go ahead and add this in here. So I'm going to go if iter, and we're going to do the modulo operator. You can look more into this if you want later. And we're going to do eval iters equals 0. What this is going to do is it's going to check if the current iteration divided by, if the remainder of the current iteration divided by our eval iters parameter, if the remainder of that is 0, then we continue with it. So hopefully that made sense. If you want to, you could just ask GPT. You could just ask GPT-4 or GPT 3.5, whatever you have, just this modulo operator, and you should get a good general understanding of what it does. Cool. So all we can do now is we'll just have a filler statement here. We'll just do print an F string, and then we'll go losses, maybe that. Or actually, I'm going to change this here. We can go step iter, add a little colon in there, And then I'll go, we'll go split. Actually, no, we'll just go loss, and then losses like that. And then we'll have some pseudocode in here. Something soon, dot, dot, dot. I don't know. And all I've done is I've actually added a little function here behind the scenes. You guys did. And all I've done soon. Dot, dot, dot. I don't know. Something soon, dot, dot, dot. I don't know. And all I've done is I've actually added a little function in here behind the scenes. You guys didn't see me do this yet.
And in the 0th element, we're going to go to message. And inside message, we're going to go to content. Okay. So all of this is going to be wrapped in an F string. So I'm just going to put this like such, and then just remove this, and then put this here. Okay, cool. So
Motherfucker. कहाँ चला गया भैंचोद? अरे
But pretty much, I'm not going to go through the actual function itself, but what is important is that you know this decorator right here. This probably isn't very common to you. So this is torch.nograd. And what this is going to do is it's going to make sure that PyTorch doesn't use gradients at all in here. That'll reduce computation. It'll reduce memory usage. It's just overall better for performance. And because we're just reporting a loss, we don't really need to do any optimizing or gradient computation here. We're just getting losses. We're feeding some stuff into the model. We're getting a loss out of it. And we're going from there. So that's pretty much what's happening with this torch nograd. And you know, for things like, I don't know, if you have other classes or other outside functions, like, I mean, get batch by default isn't using this because it doesn't have the model thing passed into it, but estimate loss does have model pass into it right here. So we just kind of want to make sure that it's not using any gradients. We do reduce computation that way. So anyways, if you want, you can just take a quick read over of this, and it should overall make sense. Terms like .item, .mean are pretty common. A lot of the other things here, like model, X and Y, we get our logits and our loss. This stuff should make sense. Should be pretty straightforward. And only two other things I want to touch on is model.eval and model.train, because you probably have not seen these yet. So model.train essentially puts the model into training mode. The model learns from the data, meaning the weights and biases. If we have both of those, sometimes you only have weights, sometimes sometimes you have weights and biases, whatever it is. Those are updated during this phase. And then some layers of the model, like dropout and batch normalization, which you may not be familiar with yet, operate differently in training mode. For example, dropout is active, and what dropout does is this little hyperparameter that we add up here. It'll look like this. Dropout would be like 0.2. So pretty much what dropout does is it's going to drop out random neurons in the network so that we don't overfit. And this is actually disabled in validation mode or eval mode. So this will just help our model sort of learn better when it has little like pieces of noise and when things aren't in quite the right place, so that you don't have, you know, certain neurons in the network taking priority and just making a lot of the heavy decisions. We don't want that. So dropout will just sort of help our model train better by taking 20% of the neurons out, 0.2, at random. And that's all dropout does. So I'm just going to delete that for now. And then, yeah, model.train, well, dropout is active during this phase. During training, randomly turning off random neurons in the network. And this is to prevent overfitting. We went over overfitting earlier, I believe. And as for evaluation mode is used when the model's being evaluated or tested, just like it sounds. While it's being trained, what the other mode is being validated or tested. And layers like dropout and batch normalization behave differently in this mode. Like dropout is turned off in the evaluation, right? Because what we're actually doing is we're using the entire network. We want everything to be working sort of together. And we want to actually see how well does it perform. Training mode is when we're just, you know, sampling, doing weird things to try to challenge the network because we're training it. And then evaluating or validation would be when we just get the network in its optimal form and we're trying to see how good of results it produces. So that's what eval is. And the reason we switched into eval here is just because, well, we are testing the model. We want to see, you know, how well it does with any given set of data from a get batch. And we don't actually need to train here. There is no training. If there was training, this would not be here because we would not be using any gradients. So, or would be using gradients if training was on.
तो 26 था ना भाई.
Anyways, that's estimate loss for you. This function is, generally good to have in data science. Your train and validation splits, whatnot, and yeah, good for reporting. You know how it is. And we can go ahead and add this down here. So this something soon will go losses is equal to estimate loss, and then we can go ahead and put and